Welcome students. In this video session, we are going to discuss about heap management. In our earlier video session, we discussed that the memory in the runtime environment is being subdivided into portions. One portion will be used for storing the target code, and the next portion is reserved for storing the global variables. And then we have two portions. One is heap and other one is stack. Now we are going to see how this heap is being managed. So heap is a portion to store the data that lives indefinitely or until the program explicitly deletes. So if you want to retain the value of a variable or an object throughout different function calls, then we can store that value in the heap. If you allocate some memory dynamically in C language, if you allocate the memory by using malloc or cloc, so those memory will be allocated in heap. Okay. Now let us see what are the subcomponents we have in the heap management. So we have a component called memory manager. So the memory manager is a subsystem that is responsible for allocating and deallocating space in the heap. In other words, it is acting as an interface between the application program and the operating system. So whenever while executing the program, we need some memory. So the request will be given to the memory manager. Only this memory manager, based on our request, it will be allocating the memory. So that is what a memory manager. So it is responsible for allocating and deallocating the space in the heap. And then we have garbage collection. So garbage collection is a process of finding the spaces within the heap which is not being used for a long time, and those spaces will be added to the pool of free spaces. Okay, so that process is what called as garbage collection. So in the heap, during the execution of the program, some memory will be allocated, some will be deallocated. So there will be few spaces in the heap which is not being used. So those free spaces, those spaces which is not being used, that will be added to the pool of free spaces. Only if it has been added to pool of free spaces, those spaces can be used for future purpose. So that process is what called as garbage collection. Now memory manager, it performs two basic functions. One is allocation and other one is deallocation. So whenever a program requests for a memory for a variable or an object, the memory manager produces a chunk of memory from the heap. Okay, so based on the size requested, it will be allocating the memory accordingly. That is allocation. Then the second function is deallocation. So here what happens is the memory manager will be returning the deallocated space to the pool of free spaces so that it can be used for future purpose. So these are the two operations or two functions performed by the memory manager. The memory manager should have some certain properties. So it should be space efficient, it should be program efficient, and it should have less overhead. Space efficiency in the sense the memory manager should ensure that the usage of heap by the program is less. In other words, the memory manager should minimize the usage of heap by the program. Okay, so in such a way that the memory manager should allocate and deallocate the spaces. And then program efficiency. Program efficiency in the sense the memory should be allocated and deallocated such that whenever a program requests for a data, it should be accessed efficiently. The program when a program requests for a data, it should not take more time to retrieve the data. So the data should be retrieved fastly. So that is what program efficiency. So the memory manager should ensure that the data are being stored appropriately so that when it is requested, it should be retrieved fastly. And low overhead. Low overhead in a sense, uh, during the execution of the program, memory will be allocated, few memory will be deallocated. So because of this allocation and deallocation, the performance should not degrade. Okay, the performance should be maintained. Okay, so that is what low overhead. So these are the properties that should be ensured by the memory manager. Then there is something called locality. Locality in the sense, the term locality refers to the point that when a particular instruction gets executed, it is more likely to get the same instruction to be executed in near future also. In a program, we may have one instruction. If that instruction gets executed, the possibility of getting executed the same instruction is more. Again, the same instruction will be executed in near future. If you want to get the point, I can give one example. In when we are writing a program with some iterative statements like for loop or while loop, the statements whatever we placed in the for loop will be executed more number of times than the other statements. In main function, you may have some statement, and inside the main function, after few statements, you may have some for loop, and for loop may be defined in such a way that it may be executed 10 times or 20 times. So the statement whatever we have placed in the for loop, it will be executed more often. Okay? There is a study which states that 90% of the execution time is being taken by 10% of the instruction. I'll repeat the point. 90% of the execution time is being taken by 10% of the instruction. Okay, so that is a concept of locality. So why we are discussing about this locality? So if a instruction is being used in the near future, then we can store that instruction in some location which is very close to the processor, so that it can be retrieved efficiently. So that is the concept of locality. This is the purpose of locality. There are two types of locality. One is temporal locality and other one is spatial locality. Temporal locality in the sense, the memory location, if you just access a memory location in which you have some instruction, the same memory location in which you have the same instruction is likely to be accessed in near future. Okay, so the point I am trying to convey is, if you just execute an instruction, the same instruction is to be executed in very nearer future, or the same instruction will be executed in nearer future. So this is what called as temporal locality. And there is something called spatial locality. Spatial locality in the sense, when we refer a instruction and we execute the instruction, there is a possibility of the next instruction to be get executed in a very near future. If you execute the instruction present in the 10th line, it is more likely to be execute the next line, that is 11th line, in very nearer future. So that is what called as spatial locality. So these are the two types of locality, temporal locality and spatial locality. Now, whenever we design the code generator, we have to address the following issues. Let us discuss the issues one by one. Input to the code generator. So what will be the input we will be giving for the code generator? We may be giving some intermediate representations. The intermediate representations can be a parse tree, or it can be a directed acyclic graph, or it can be a tree address code. Okay, it can be anything. So the entire code generation is based on the input what we are giving to the code generator. Okay. In addition to the intermediate representation, we will be also giving symbol table as input to the code generator. Okay, so this is the first issue. And second thing is the target program. The code generator will be generating an output, and that output is what we are calling as target program. And there may be three type of target programs. One is absolute machine language, or it can be relocatable machine language, and the third one is it can be assembly language. The target program generated by the code generator can be any one of the three types. It can be absolute machine language or relative machine language, relocatable machine language, or it can be an assembly language. Absolute machine language in the sense the code, the target code, whatever that is being generated, it can be stored in some location and it can be executed. Directly it can be executed. So such target code is what called as absolute machine language. In case of relocatable machine language, the instruction, the target code, whatever that has been generated, it can be relocated to some location and it can be executed. That is what relocatable machine language. And the third type is assembly language. Assembly language in the sense the target code, is an assembly code. So that assembly code should be processed by an assembler. So again, you need one more component called assembler, which is going to process the assembly code that is being generated by the code generator. So we have to decide whether we need absolute or relocatable or assembly language. Then the next one is memory management. So memory management in the sense it is a mapping process. It is a mapping process between the logical address and the physical address. When we generate the code, in specific, when we generate the 3 address code, we will be having the identifiers, and these identifiers will be referring to an entry in the symbol table, and only in the symbol table we will be having the location where it is. So those mapping process also we should be taking care of. So that is what memory management. Then instruction selection. So for a particular instruction, for a particular intermediate code, we can generate the target code in different ways, but we should generate the efficient one. Say for example, we have a statement like R is equal to num1 plus num2. This statement, this intermediate code, it can be represented or it can be converted into target code in n number of ways, but we should generate an efficient one. So that is an challenging task. That is another issue, instruction selection. Then there is something called register allocation issue. So the purpose of register is that in order to improve the efficiency of the program's execution, we will be storing the values of the identifiers in registers. Okay, we may have some variables in our program. So those variables, instead of storing those variables value in system memory, we will be storing those values in registers. So what is the purpose of registers? When you store it in register, obviously the processor can retrieve the value efficiently, because the register is a memory that is available within the processor itself. So it can retrieve the values efficiently instead of retrieving the value from another storage device. It can efficiently retrieve it from the registers. Now the challenging task is we have to decide what are all the variables we have to store it in registers. Not all the variables we can store it in register. So we have to select the variables which can be stored in register. Not randomly we can select and store in register. Okay, we have to select the variables which can be stored in register appropriately so that the program efficiency will be improved. So that is what register allocation issue. And the next issue is evolution order. When we have the instruction, this instruction can be executed in different order. Okay, so what the code generator should do is the instruction should be selected in a particular order so that the program efficiency will be improved. So in such a way, the statement's evolution order should be selected. And then comes approaches to code generation. So whenever we go for code generation, it should ensure that the target code, whatever that is being generated, is correct. The target code, whatever it is generated, is easily maintainable. The target code is testable, and also the target code generated is an efficient one. Okay, so these are all the issues involved in designing of the code generator. With this, we are just moving to the final topic, that is generation of simple code generator. How to generate the code. So we have an algorithm for it. Now we are just going to discuss the algorithm with a simple example. Now let us assume that we have an instruction x equal to y operator z. Okay, so we have a 3 address code like this. X equal to y operator z. Operator can be anything, plus, minus, multiplication, whatever it may be. Some binary operator. So y operator is. Now for generating the code for this 3 address code, we have to follow 4 steps. The first step is we have to invoke the function getRegister to determine the location L where we will be storing the result of this. So the first step is to create or determine the location. Okay, we have to determine the location of the register. Okay, so where you will be storing the result of this operation. Okay, so for determining the location, we will be making use of a function called getRegister function. Okay, this is first step. A second step is we will be consulting address descriptor. Okay, we will be consulting address descriptor for the operand y to determine y dash. Okay, so address descriptor in the sense, so address descriptor will be having an address of a particular variable. Okay, sometimes the variable value may be stored in main memory, sometimes the variable value may be stored in register, or it may be stored in some other location. So wherever it may be stored, that address will be tracked by the address descriptor. So address descriptor, when you just request address descriptor for y, it will be telling where the current value of y is. So that is what address descriptor is. So we have to consult the address descriptor for y to determine y dash. Y dash is the current location, the current location of y. Then we have to ensure that we have to prefer that the y dash should be a register. Okay, so y dash is a register instead of main memory. Y dash should be register. Suppose if it is not in register, we have to move it to register. Okay, so by using the instruction move y dash comma l, you have to move the y to register. Fine, this is second step. Then the third step is we have to generate the instruction operation z dash comma l. Already we have y dash in l. Now we are just performing the operation. Operation z dash comma l. We're just having the instruction. We're just generating the instruction. Operation z dash comma l. What is z dash? It is a current location of z. Okay, so it is a second operand. Okay, the first operand is y. Already we moved y to y dash. Y dash in the sense y dash will be in register. Then we are just generating the instruction operation z dash comma l, where z dash is the current location of l. Now, once if you perform this operation, okay, what happens is the operation will be performed on these two operands, and the result will be stored in l. Okay, the result will be stored in L. So next, after storing the result in L, what we have to do is we have to update the address descriptor of X to indicate that X is in location L. Why we want to update the address descriptor of X? Because in the instruction we want to store the result in X. So we performed the operation and we store the result in L. Now what you have to do is the result whatever we have in L, it should be assigned to X. So that is what, update the address descriptor of X to indicate that X is in location L. Okay. So this is the third step, and the last step is that once if we don't need Y and Z anymore, we can deallocate the space. Deallocate the we can just remove Y and Z from the registers. Okay, so for that we will be making use of register descriptors. Okay, so these are the steps we have to follow for implementing the code generator. Thank you, students.